All right. Hi, everyone. My name is Michael Pani, and welcome to our fall workshop, a shooter mechanism from concept to competition. All right. Who's going to introduce themselves next? Mackenzie?
Sure, I can go ahead and introduce myself. Hi, everyone. My name is Mackenzie. I'm from Team 2073 Eagle Force Robotics. Currently, I'm the mechanical director on our team, and this is my, as far as our 2020 robot, I was mainly involved with CNC machining. I also did some assembly and I started with a little bit of our CAD work, but my main focus was definitely CNC machining.
All right. Hi, my name is Gurvir. I'm the 2073 programming director. I worked on the Limelight and shooter calibration, and I worked on a lot of the software behind shooter-related mechanisms such as the turret. I've been a member for 3.5 years, and robotics has been, an amazing experience, as you can see from the pictures on my slides. Yeah.
Hello, my name is Matthew. I am the Team 2073 Programming Manager. As far as this past year, I mainly worked on the turret and limelight code and testing and other mechanisms on the robot. I also worked on the wiring for the shooter and other mechanisms. I have been a team member for around 3.5 years now.
That'd be me, but I already went.
Hi, my name's Tanner. I am an alumni of Team 2073 Eagle Force Robotics. I worked on robot design in 2020 as well as CNC machining in 2020, and I was a team member from 2017 to 2020.
All right. Now we're going to watch a video.
Hello, we are Team 2073 Eagle Force Robotics, and today we're excited to welcome you to our shooter mechanism from concept to competition, our in-depth look at 2073's process for building a competition robot. In this video, we will be going through our process for prototyping, designing, building, and vision tracking on our 2020 season robot. In an effort to simplify this video, we will be focusing on our shooter and how we went from a single idea to an operational mechanism. However, our design process can be implemented for any part of the robot. The first week of build season is probably the most critical time for a robot. Like many other teams, our team attends our local kickoff event in January, where we watch the reveal video for the very first time. On that first day, we don't start with designing or building. Instead, we focus on understanding the game and its elements. By first reading the game manual and then creating and passing our team's rules test, we can move on to what an alliance, and more specifically, what a robot needs to accomplish in order to win. We knew from the start that we wanted to be an offensive robot, and that meant prioritizing 3 main goals in this order. Number 1, climb. Number 2, shoot in the high goal. And number 3, spin the Wheel of Fortune, or aka the control panel. If your team came up with a different order or different goals, that's okay. There are many examples of robots specializing in 1 or 2 parts of the game with great success. Most notably, Team 1011 in 2017 and Team 2910 in 2019. These 2 robots highlight the importance of good strategy and sticking to your goals, something teams at all levels need to do. For us, climbing was the most important part of the game this year because this is the single task with the highest point value, netting up to 40 points solo, 25 for the hang, and 15 for the switch. If completed in balance with an alliance partner or 2, you can earn 65 to 90 points, also earning your alliance a ranking point. It is this type of game analysis that should be done for every aspect of the game before you start building your prototypes or your full robot. We used a similar process when addressing how many balls we wanted to shoot for each round. as well as for our autonomous run. Our team then went from these strategies to hypothesizing possible mechanisms to achieve and complete these goals. The bulk of our strategizing revolved around scoring as many balls as possible. We believed that this would be the difference in matches where every robot could climb and spin the control panel. In order to score balls quickly, we believed we needed to hold 5 balls, be able to travel underneath the control panel to avoid traffic, and have a straight line to complete cycles. Additionally, for high-level play, we found it beneficial to shoot from anywhere on the field and over defenders to continue scoring points in eliminations. These strategies provided plenty of restraints on our robot design.
Now that Mackenzie has laid out what we want our robot to do, it's up to the design team to figure out how we can get it done. If you have ever tried to design something from scratch, you most likely know that this is a difficult task. Each year, we look to previous games for inspiration from other teams' successful components of their mechanisms and try to incorporate them into our robots. Teams such as 254, 1678, and 971 are a few we like to reference. For example, a certain shooter type that is repurposed in Team 254's robot designs throughout the years is a flywheel shooter. In past years, 254 has utilized an adjustable hood to score from many field locations. On our 2020 robot, we used a similar design that supported our shooter that fit their needs for each season's tasks. Team 254's flywheel shooter is a great example of how you can recycle ideas for a new season in order to satisfy your current game objectives. By watching matches from past games, our team was able to see which mechanisms, like this shooter, were effective in order to implement them into our 2020 robot. Sometimes there's no need to reinvent the wheel.
Now that we know what type of shooter we intend to make, we need to determine the angles and speeds that we intend to test with our prototype. Using tools found in JVN, we input information such as the weight of a mechanism, the number and types of motors it uses, and the gear ratio it uses, which JVN uses to calculate the speed and torque of the mechanism. This allows our team to determine if the chosen gear ratio is effective for the mechanism before having to test it on a prototype. We cannot stress enough how important it is to use a design calculator like JVN to save your team time and money. Our design team had already narrowed our gear ratios down to either a 2-to-1 or a 3-to-1 ratio using JVN and other calculations. The 3-to-1 ratio would give our shooter more torque but less top speed. Alternatively, the 2-to-1 would give it more top speed but less torque. The more torque a mechanism has, the quicker it will be able to reach its max speed. But our speed was a constraint on the shooter mechanism because we needed a high enough speed to be able to hit all of our shots, but we also needed a lot of torque to be able to reach that speed quickly. As a result, we prototyped both a 3-to-1 and a 2-to-1 shooter to determine which ratio would be best for our goals. We decided to use the 2-to-1 due to its higher speed, giving us a further range to shoot from, with the compromise of adding a third motor to the shooter for added torque. When determining the shooting angle for the hood, we used the 2019 shooting trajectory calculator in order to determine the most ideal angle. We knew that we wanted to be able to shoot consistently from as far as the control panel, so we took the distance of that spot and other desired positions and inputted them into the spreadsheet. We then inputted the dimensions of the target, the max velocity of the shooter, and the height of the shooter. Using these inputs, the spreadsheet determined a suggested velocity and angle. We found the dimensions for the target and distance it is from the control panel in the FRC game manual, and used CAD to determine the height of the shooter. Using the spreadsheet, we then found a general angle that worked for any distance between 6 and 30 feet. Using the accuracy predictions, we were able to play around with the theoretical launch speed. We did this because we knew it would be easier to control the velocity of our shooting mechanism versus fine-tuning the controller for launch angle. The link to the trajectory spreadsheet and JVN are shown on the screen above and are going to be linked below.
We follow a clear design process our team has developed over 13 years of competing. We have put together a document with more information about our design process. If you are interested, linked below. What's the objective? Our team, as stated at the beginning of this video, identifies the objectives, scores, cycle times, and roles you want to play within the matches. By setting our strategy early, If we want to play certain roles, such as filling the rocket for a ranking point during Deep Space, the game of 2019, we are able to plan our subsystems to match those needs. Example: our shooter was intended to shoot and score in the outer port near the top of the space station. So we had to design our shooter accordingly, so it can compensate for a much greater height at certain distances, which made us keep angles and projectile trajectories our shooter would enforce when it was constructed. With our big goals now reinforced with many calculations, models, and inspiration from many other designs, we look to our prototype to understand unforeseen challenges of the current game. These challenges are to be expected with the ever-changing competitions and strategies of FIRST. For example, an intake that worked in 2018 on the 13-inch power cubes is not going to be as effective in 2019 on the 13-inch cargo. This year is no exception. Still unsure of optimal compression and wheel materials, research and testing needs to be done. Then, once we know the challenges, we build solutions to nullify them. So we want to back it up with information, inspiration, and innovation from other teams' mechanisms. Having more knowledge from other teams' trials, experiments, and data with different approaches to a similar problem makes our design process much easier, as our mechanical and CAD team can start and finish parts faster and start improvements faster as well. Create. We make a prototype to test the fundamental questions like distance, accuracy, balls per second fire rate, compression, and materials we have in regards to our initial designs. This is crucial to the design process because it's needed to verify any questions or theories that would be relatively plausible prior to the prototype. It's essential to have a great prototype, as it is made carefully to yield the best results and provide more accurate information from testing on it, because whatever mistakes happen on this prototype, you can fix before it is replicated on the robot, saving time, money, and resources. Our prototype looks like this. And the aspects that we incorporated when we built this prototype were, for the shooter in particular, we were confident that it would work based on past experiences with shooters. Looking at these shots and speeds, we were then able to look toward improvements to our hood system. For example, we learned when the ball would exit the shooter, the hood would tilt upward, increasing our launch angle. To account for this error, the mechanical team reinforced the hood to ensure that we were shooting at a consistent angle. Test. Once the parts are made, they need to be tested. The reasons we included for the mechanism we make and why we made it directly correlate to this stage of the design process. The objectives we made for scoring certain points, fulfilling certain roles, etc., have to be fulfilled with the mechanism that we designed. Therefore, we test the subsystems on field elements that our team constructs. We test the speeds, consistency, and cycle times of various components. As you can see, our programming team is hard at work shooting at different distances, angles, and power to calibrate and configure the most ideal conditions for our drive team to secure the competition with as many possible points. Improve. Naturally, with those tests, many things can happen. In fact, on several occasions, parts and systems on our robot have broken, failed, stalled, or fallen short of their intended goals, and this has happened many times. Frankly, this is the best part of the design process, because we find out what was wrong with the prototype when it was constructed, and target our improvements on preserving the strengths of our parts but getting rid of the weaknesses. For example, with our hood, it was too flimsy, so we added strings to help stabilize the hood. We look at what issues there are with our mechanisms, and brainstorm creative solutions to accommodate them. But we wanted to test the hood angles, gear ratios, wheel type, and option that worked the best to get a powerful and accurate shot. These benefits showing why we incorporated these in a prototype now, rather than seeing those issues and conditions come up much later. Using the launch angles determined in the prior section, we spent time testing the shooter from a wide assortment of shooting distances, testing the reliability of the angle and the RPM the motor would be set to consistently to make a shot.
When it comes to designing our robot, each year our team relies on Autodesk Inventor. As mentioned previously, we like to have a solid plan for a robot before we start manufacturing parts for it. So, using CAD to virtually design a robot is extremely important. Not only does it help us visually see what a robot will look like, but it also allows us to predict the weight and the height. This is essential because it allows us to reevaluate and adjust parts of our robot if necessary. We try to create a robot with as much accuracy as possible, making sure to CAD our parts for clearances and even including bolts into CAD. We also include wires, and we account for any miscellaneous weight at the end. While this may seem like a lot of work and very repetitive, it helps our mechanical team get an idea of how much our final robot will weigh and allows us time to troubleshoot any collisions that a bolt head or any other parts may cause. Our CAD can also be extremely useful for if something on a robot breaks. We can easily pull up a model of a robot and figure out what went wrong, what was missing, and what broken parts we can repair. This is much easier than guessing or having to redesign a whole part. After we came up with a basic idea of what we wanted our shooter to look like, we started fabricating a model. Our first iteration of the shooter was made mainly out of wood and was supported by a set of chairs. At this point, we were testing our hood and wanted to make sure that it would shoot properly. We weren't worried about the cosmetic design. We used the Fairlane wheel on our prototype because we knew it would stick to the ball and would still functionally work. However, on our final model, we switched to stealth wheels because they were lighter and didn't expand as much. We also prototyped an adjustable hood and turret that would enable the robot to shoot from anywhere on the field. In the end, we bolted the hood to our final turret ring, which uses a servo on a link arm to adjust our shot that slides the hood up and down a set of bearings. A lot of our other prototyping for the hood was testing which angles would work the best and specific places on the field. A few of the other big changes we made from our prototype to the final model was adding a motor, flywheel, and finally gum foam. Just like CAD, prototyping is essential to our building process. Each year, we have multiple people working on separate prototypes so we can see which ones will work out the best. Sometimes a prototype may work well, and all we have to do is switch it from wood to metal. Then our mechanism is practically done. But more often than not, our prototypes go through multiple iterations before we can decide on a final and functional design.
Vision opens up opportunities to fine-tune the actions of the robot to its environment. It allowed our shooter to respond to height, distance, and the angle away from the target, proving a crucial element in our turret design. The limelight allowed us to locate our target throughout the field at a variety of positions. The limelight documentation was an extremely helpful resource and consolidated information that we needed for code development. Documentation provided information on distance calculations needed for our logic and contained basic information on determining if it had a visual on the target. Occasionally, the information relayed from the limelight would provide incorrect values, so some additional logic was incorporated to filter the data we received to ensure the data was consistent. The distance the limelight provided controlled the elevator's height and the RPM. Using our testing, we programmed when the robot should rise depending on the distance and used linear interpolation between our data points to determine RPM. Also, the angle of the limelight placement influenced the distance calculation and determined the relative ease to which we could see the target, which is why it is necessary to pick an effective placement. We chose this angle because it allowed for us to see the target both up close and from far away. Additionally, you want an effective launch angle for the shot to maximize the chance of hitting the target. Using a spreadsheet we found on Chief Delphi, the programming team determined an effective angle for our hood. The mechanical team then placed a hard stop at the extended location to ensure the reliability of the servo instead of relying on tuned programming values. However, the bottom angle of our servo is determined through code because programming was able to find a more effective bottom angle to shoot from. Because the height of our shooter was dependent on the elevator position, we utilized multiple pipelines for the limelight to ensure the calculated distance was accurate. Additionally, it is important to note the distance calculation is affected by the height of the limelight. Information on creating pipelines can be found on the Limelight documentation on their website. Pipelines allow you to tune the image that Limelight receives so you can have a clear and accurate image for different placements and situations.
We hope you enjoyed our in-depth analysis and explanation of our shooter mechanism. If you want to see more videos like these from Eagle Force Robotics, follow us on Instagram, subscribe to our YouTube channel, smash that like button, leave a comment below for what you'd like to see us do next. Best comment gets pinned. See you in the next one.
All right. So we have a Kahoot. So that'll be showcased right here. The code's up there. So the code's 7396574. So if you guys want to participate, please join, and we'll be going over through some questions, some common questions, and explaining them with members of our programming team and mechanical team. Sounds good. Okay. We'll just wait, for a minute, make sure everyone gets in that wants to, and then we'll start it up. There were 63 people watching, right? So there might be a lot of people joining the Kahoot. All right, 23. Is that it? Or okay, we'll wait. Yeah. Oh, Jeevan and Josh, they joined. Yay. All right. I say another 30 seconds and then we should start it, right? All right, let's start it. All right. Turrets are fun. If they work, when they work, they're fun. And when they break, they make you cry. Yeah. Personal experience. Not crying, but turrets breaking. All right, okay. So our turret, we used it to shoot from any angle on the field, like in front of ourselves. So turrets, they can be complex to program and design. That's why it's not an advantage of having them. But being able to shoot from any specific angle is an advantage, and a lot of people selected that. And that's why we chose a turret specifically for our shooter, because we could be at an angle and our turret can move to hit the shot. So that was our reasoning on that, having a turret. Anyone want to add anything? Matthew, Tanner, Mackenzie, any additional thoughts?
You pretty much covered it.
All right, so let's move on to the next one. All right. Next. All right. True or false? When designing a mechanism, it is important to look at designs from past years. All right. So mostly everyone got that right. Anyone have any comments? Oh.
So when we were designing our shooter this year, we definitely looked at mechanisms from past years. That was something that really helped us get inspiration or have an idea of what worked before and what we could implement that would most likely work again this year.
All right. Next question. Oh, this is one of my favorite questions on the Kahoot. Extra credit, who can guess GVBB? In the YouTube's comment section or live chat. If someone can guess it, extra credit in my mind. All right. Yeah, so we use JVN. Mackenzie and Tana can speak to that.
Mm-hmm.
All right. Also, we had a fabrication question after this one. So the question was, do you guys CAD each wire individually, or is there an automated method to make that process faster, less tedious?
Each wire, you said?
Yeah, so the question was by Jayton Sony. Sorry if I mispronounced your name, but it's asking, do you guys CAD each wire individually, or is there an automated method to make that process faster / less tedious?
We actually don't CAD our wires. I know we use Inventor, which isn't set up very well for CADing wires in particular. I think SolidWorks is a little bit better for that, and there's some other CAD programs that are better for CADing wires. But we choose not to CAD our wires, and it works out decently well for us.
So let's move back to the Kahoot, right? Any comments on JVN, or should we
I don't think so.
continue?
I think the video covered most of it. Yeah.
All right. All right, let's move on then. All right. Ooh, big change. GVBB comes back on here, so yeah, the offer still stands. Extra credit if you guys guess that. Yeah. Yeah, computer's useful, but you need a lot of my documentation to actually use it effectively, right? So kind of a trick question, but yeah, me and Matthew relied a lot on Limelight documentation, especially when we were looking on how to relate the Limelight input into turret position. So based on what the Limelight would see, we'd move the actual turret based on those angles and if the Limelight had it in sight. And so Limelight documentation has a lot of resources for that. They have some code examples in C, and so we convert that to Java and whatnot. So yeah. Next question. I believe Tanner mentioned this earlier, but yeah, with the wires question. Oh, yeah, also that Limelight, yeah. So what happened was, so basically, yeah, Bill pretty much put it into, explained it perfectly. Limelight, we were doing autonomous code. goes straight into a desk and just breaks the limelight. And so, we want to highlight, limelight issues. Breaking limelights is an issue. They're $400 a piece. So we want to minimize damage to limelight and, ensure proper safety for our team. That's why we had desks. So it was good that we had desks lined the edge in case our code did fail. We made sure that there's proper safety precautions so no one got hurt. And so only the limelight got damaged. No humans did. And so yeah. And this question right here, Tanner and Mackenzie can comment on that.
Yeah, I think Tanner talked about it earlier about how we use Inventor. I know a lot of other teams might use SolidWorks. Onshape, I think just because of the current situation, a lot of people have been using that recently. We use that in our classes at school, but for robotics, we rely on Inventor.
Wait, Michael, your team uses Onshape, correct?
Yeah, we have used Onshape for the last year, and I believe part of the year before that. We switched
Okay,
over
nice.
from SolidWorks just because of the online aspect.
Okay, cool.
Makes sense.
Yeah. Next question. This is one of those small details I mentioned earlier in the video. Yeah. So mechanical team. Let's quick recap. Or Matthew, you worked on that section, right? On the gear ratios that we specifically chose. So
So we used a 2-to-1, and the reason for that is it gave us more speed. We really wanted to be fast when we were moving around on field, when we were shooting, so it gave us more speed in our shooter. So that's why we used 2-to-1. That was kind of the advantage it gave.
yeah. The disadvantage was we got less torque, as you mentioned in the video, but that's why we added the third motor. So initially we were using 2 motors, but then to get that additional torque that we lost, we added a third motor. So that was a compromise that we had to make for the greater speed. Next question. Oh, this is a hard question, dude. Really hard question. Tanner has a joke about this section. I'll have Tanner explain it. Yeah, Bill, we could get the links mentioned in the video posted here. Let me grab some. Yeah. I have to go into Google Docs real quick. I have some link there.
Yeah.
Okay, you got it? Okay, perfect. All right. So Tanner can explain this one. Tanner has a really good point here.
I honestly don't remember the joke you're talking about, but for this question, obviously you eventually have to move on from prototyping to making a final design if you have a deadline like FRC does. However, the idea is that you never stop prototyping. So even the design you use on your robot, you can go back and change after each competition, especially now that there's no bag day. So that's why move on is not necessarily part of the prototyping design process, because really you're never truly moving on from prototyping. You're always prototyping.
Also, we use 775 pros, right, for our shooter, correct? If I remember.
That is correct. We used 3 775 pros on a 2-to-1 ratio to power our shooter.
Yeah. All right. And okay, so next question. Let's get this show on the road, all right? This was the amount of times this material would break was annoying. I remember being in the workshop, trying to get a stand made for the limelight to test different angles on. But yeah, using this material, and I suck at using this material. Yeah, wood. Yeah, splinters when you nail it, or when you screw it, splinters really terrible. But our mechanical team did a good job of prototyping a lot of stuff in wood, and making do with that. Any comments on that process?
I don't think so. I mean, in the video, I think it was shown maybe twice of our prototype that was made out of wood. You could see that it was definitely different from our final design, but it was just great in getting our team to be able to test it to see if it would work in the first place. So that's why we chose wood. It's also cheaper than using aluminum.
So next question. All right. Yeah. So advantages, guys. So yeah, so our hood allowed us to adjust our shot angle, and being able to adjust our shot angle allowed us to shoot at further distances and close distances as well. There's also a question for the mechanical team. Why did we choose 775 Pros over Falcons? And with the Neo motor for the turret, how did you keep track of turret position? So I can answer the turret position comment. We used the built-in encoder and the potentiometer as well. So we had a potentiometer on the turret that we used to monitor position, and we also had used an encoder on the motor to keep track, and we sync those two up and use that effectively to uh, keep track of our turret position and make it go to specific endpoints. And then with the 775 Pro comment, Mackenzie and Tanner can answer that.
Yeah. So we chose to do the 775 Pros for quite a few reasons, actually. First of all, the Falcons are new motors. They were very difficult to obtain right at the beginning of the season, so we couldn't prototype with them. We did end up using, I think, one on each of our robots, but they were difficult to obtain. They're new motors, so weren't sure of their capabilities quite yet. We had the numbers, but we didn't have the ability to test to back up the numbers. On top of that, pros are smaller. They were easier to package on the small shooter we wanted to make, and they have a much higher RPM, which means we could effectively gear them down as opposed to the Falcons where we could gear them up. Now, knowing what we do about Falcons with, I guess, half a season of testing, we would maybe want to switch to Falcons in a later prototype. So there's advantages and disadvantages, but Falcons are very, very good motors. We just decided to use pros for personal preferences and a lot of packaging.
Yeah. So let's go to the next question. All right. Oh, okay, this goes hand in hand with the last question. Matthew, this is a multi-click question. Yeah. Okay.
Yeah.
All right. So yeah, so the purpose of having that adjustable hood was so that we could have shots up close. Like as you saw in the video, we had shots like right up against the shooting the target, right? And then we'd also have shots, down the trench, by the Wheel of Fortune or control panel. I remember that's the proper name, but yeah. And then the adjustable hood gave us more flexibility in our design because we weren't fixed to one specific launch angle. We could manipulate that launch angle, and if you've taken physics, 2D kinematics, it's very important in that aspect. And our spreadsheet that we used to calculate the angles also showcased that how the launch angle did affect where the ball went, right? So that's an important reason why we use the adjustable hood. So next question, right? Let's move on to the next clue question. Yeah, so this was a part of our strategizing at the start of the season where we wanted to maximize the amount of points we got. So playing defense wouldn't really maximize our points. Sure, it's an important skill to have, but to increase the chance of winning, we wanted to be able to spin the control panel. We wanted to be able to shoot into high goal, which is the big section of the target. 2 points for the outer, 3 points for the inner. And then being able to climb was also effective because ranking points, and then I believe it was 15 points per climb, or am I mistaken? It was a big point value though, and so we wanted to ensure that we maximized the amount of points we got in game, and that we were a top tier robot. So moving on, right? Make a broken record. Said it like 12 times already. All right. 5, 4, 3, 2, 1. All right, let's see this. All right, everyone got this one right. So I assume everyone understands that prototyping is very important. We use it effectively and important tool set. So next question. All right. Moving on. All right. Perfect. So yeah, CAD shouldn't be detailed. I'm gonna give a hint on this question with the wires answer, but yeah. There's only 17 people responding, right? So we don't have to wait the rest of the 10 seconds. Once we get 17 answers, yeah. Okay, yeah. So you want to have it have some detail. Mackenzie can definitely speak on this. So I'll have Mackenzie and Tina speak on this because they're more experienced with CAD. So I'll step back.
I can't speak on this question. I actually have a workshop that I have to join that starts in 10 minutes, so I'm gonna actually leave right now. So everything's gonna be put on Tanner. Sorry about that.
All right.
Okay.
Bye.
Bye, Mackenzie. Yeah. So yeah, CAD should be as detailed as it is worth time to do. We put a very big emphasis on that with our team of CADing every single bolt, every single hole on the robot, right? With the thing about wires, even though we don't CAD wires, we still put a big emphasis on placing all of our electronics exactly where they're going to go on the robot. We just don't CAD wires because Inventor doesn't have like the best capability of doing that. But if you can CAD wires, you definitely should.
All right. So let's go on to the rest of the Kahoot. Multi-select. Okay. The limelight light does look pretty though. Like the big bright green light that blinds you. Nice and green. But yeah. Hurt my eyes a lot during the season. Messing around with limelight. Prototyping was a big part of that, making sure we had the right angles. We're shooting properly with the limelight. And so a lot of times you accidentally got hit in the eyes with the light. And limelight's super bright. Alright. So as I mentioned in my section in the video, limelight allows us to have more precise shots. It allows us to give feedback to the driver if they're out of range or if they're too much to the right and the turret can't make the shot. Or and we can also calibrate the shooter speed. That's what the interpolation was for. The limelight would give us a distance back, and depending on that, it'd ramp up the shooter to a specific speed that would increase your chances of making the shot. So that's my reasoning there, and those are the advantages that we saw that were effective with using limelight. If Matthew has some comments, he could also mention that.
No, I think you covered pretty much the benefits of limelight.
All right, so we have 3 more questions. Let's get those wrapped up because we have 8 minutes left in the video. So yeah. All right. All right. So Tanner can definitely talk about JVN. He's used it a lot as a member of the design team.
Yeah, JVN is a very, very good tool for gear ratios. It's a very good tool to determine torque and speed and all of the math stuff. The angle of the shot was actually calculated using a different program. That was in the video. I think Gurvir and Matthew can talk a little bit more about that. But JVN doesn't give you the angle of the shot because you need a whole bunch of other math to be able to do that. However, in order to determine what speeds we needed, we had to use JVN, so we had to use both programs.
Yeah, so the spreadsheet we found is on Chief Delphi. Really good tool. It allowed us to plug in the distance we were away from the target, the height of it, and then we could play around with different launch angles to find like a consistent launch angle that worked for like different speeds. Because we knew that we could easily change the speed, but we don't have to manually change the angle all the time. But having the adjustable hood still gave us some degree of freedom there. But we didn't want to rely on that as heavily as our shooter's speed control. So yeah. So next question. All right. So yeah, obviously prototyping's very big. You can find out what works, what doesn't. Prototyping was how we figured out that we wanted a 2-to-1 versus a 3-to-1, and it allowed us to figure out what speeds we needed and how to fix our different mechanisms. Like the adjustable hood, we did 2 versions of that, correct, Tanner? Did we revise? We revised the design, I remember it, but how many times did we revise the design through prototyping?
We had 2 different adjustable hood designs, and then like for each of those, we had 3 different angles we were testing.
Okay, and then yeah, so prototyping's big. We figure out what works, what doesn't, and then the final question in the Kahoot. Quadruple motor shooter. That's a mouthful. Yeah, sounds good. Yeah. Quick answer, quick response. So yeah, we use the flywheel shooter because we have those 2 flywheels on the side that allowed us to preserve inertia. Tanner can go into the physics of it and why we chose that, right?
Yeah, we chose a flywheel shooter because it had worked for us in the past, and we had room to put 2 big metal flywheels on the outside. I don't know if you guys saw a lot of the pictures of that, but that allows us to keep the momentum and the inertia of the shot, which means that when we shoot one ball, the shooter doesn't slow down. It keeps going because it just has so much weight behind it. So when you shoot one, it doesn't slow down. So when you shoot the next ball and the ball after that and a ball after that, they all hit the exact same place because the shooter is spinning with the exact same speed. If you didn't have all that weight behind it, then the ball could slow down the shooter.
Yeah, so that's our presentation on a shooting mechanism from concept to competition. I think we have a minute left, so if anyone has any questions, leave it in the YouTube comments section, or if you want to reach out to us, I believe our contact information is on the Capital City Classic website, so check that out as well.